So we start up. It's well, before we begin, one information for you. If you have started now forming student groups, but you are not 4 yet, you are maybe 2, or you are maybe 3, or you are maybe 1. But if you have an idea for a project work, or if when you get an idea, tell me, and then I can grant you access to the stage here. You will be given, say, 1 minute. That should be enough. You just make a principal sketch on the blackboard and tell the audience your idea, and then ask, will somebody join me for this project? So in a couple of weeks' time, then I will open up for this to happen. I will tell you in advance, but there you can then recruit members to form a group. Okay? But that would then be, say, in a couple of weeks' time. Now, an example. We are talking about response system. So, say, what should we call it? Frequency due to the response. And I make an example as simple as possible. So here I have a plate, and he can move up and down with a certain velocity, say y something. And then we have a spring, and then I have a mass. No damper. No damping in this system, which is, of course, terrible. But never mind that. Gravity, you can add gravity for this problem if you like, but it doesn't change anything. So here we can just say, I don't have a gravity. And then what is going to happen? The velocity for this plate is given. So we know the velocity. Hence, this is going to be a flow source now hitting a spring that is a 0 element, and then we have a 1 element with, it has its own velocity, and it has mass, but it will be simplified to this graph here. Flow source, causal stroke should be like this. Well, for a 0 junction, that doesn't dictate anything, but when I choose, say, for the C element, then the I element also will obtain the integral causal strokes. So what will be the equations here? Now you see it's a second order system. You have 2 elements, energy storage elements, on the integral form. So we will have 2 equations out of this. Here I know the velocity for this plate, the flow source. I don't care about the force needed to do so. Here I will have a q dot circle, q over c. Here p dot circle, p over I. And then the entire bond graph has been annotated already. Where's the equations? Well, we have a common effort. So the force is the same all over the place here. And the only force that I have is q over c, has then to equal p dot. So that's one equation. The other equation you find by using the summation rule around the 0 junction. Sum of all flows has to be 0. So q dot, he goes out, equals what comes in. What comes in is the source minus p over I. So there you have your equations. Now, what kind of system is this? Let's see if we have some system here. Yeah, here we have something. Here we have a system. So now I just turn it upside down. That doesn't matter. I don't have gravity into the problem anyway. So I have a spring and then a mass. So now if I give him some input, then he will start to move. And then, of course, it depends on the input I give him. The first thing, typically what you would be interested in, is what's this system's natural frequency? Natural frequency, how to find that? Well, for a natural frequency to anything, you give him a kick and then he moves. Then you see the natural frequency. Same with this one. Give him just a kick and then you're talking a step, unit step input. So you just move it a little bit and then you will see his natural frequency. So that's the response for a step input. Step input, you will see the natural frequency. Next, you can try with a sine wave input. Harmonic input, sine input. And then it's a question at what frequency? So here, if I now start keeping him still, if I move my hand in a harmonic way very slowly, then I have a very low frequency. Very low frequency. So then the spring will sort of be constant. The mass will move just parallel to the ground or to my arm. So moving this one now in a harmonic way, the mass will just follow the ground, you might say, if you do it very slowly. If you do it very fast, then you're doing it so fast that the mass, he doesn't have time to react. The mass doesn't move at all if you're fast enough. Same will be here. Way too fast, and the mass he's just staying there. But if you hit or are getting close to the natural frequency, then what happens? Of course, then you are talking resonance. So for a system like this, you only need very small input if you are hitting the exact natural frequency. You see my hand is hardly moving, but now the amplitude is going to explode and the system breaks down. So response, you hit the natural frequency for a system. Let's see if we can visualize this. Here I now have my plate downstairs. It's red. I have my spring green and the mass blue. This line of circles, they are just sort of a timeline going now to the left, giving you the position. So then we start with a step. Step response. You have a slow computer. So there you see one kick, and then the mass now will move very nice way in its natural frequency. And then I start with sine input. So now the plate is moving with a harmonic motion, and now it's very slow. You see the ground frequency is 10% of the natural frequency of the mass. So he's more or less parallel with the ground here. Now we are at 50%. And then you see the amplitude there for the mass is getting bigger than the amplitude of the signal that we send in. At least sometimes. Sometimes you will have sort of the damping out. You zero out the total force or the acceleration for the mass, so we were standing still for a period, but then you will really jump up. Now we're hitting the natural frequency directly. So here the system breaks down. Remember, I have no damping in this system. He's getting really high here. So now, of course, this ratio, the amplitude of the mass divided by the amplitude of the input signal, is exploding, goes to infinity. 50% above the frequency, the natural frequency. Again, the amplitudes, they are bigger than the input amplitudes, but not too much. And now 5 times the natural frequency. So here the ground is moving so fast that the mass can hardly follow him. So the amplitude for the mass there is quite small actually. Here if I tried with even faster frequencies, but then the numeric broke down, then you need quite more advanced, more accurate numerical schemes to find the position for the mass. So I didn't bother. At least you get the idea. Any questions to that one? I'll put out the source code here so you can have a look at it. It's a quite okay trick in MATLAB when you want to do animations. I can show you. Shouldn't take too long. Say when you have a graphical window like this, you can produce a line here. Let's say, what do we have? Take a big H equals line. Now the notation for a line, you need some x positions. X can go from 0 to 1. Then y have to go from, say, 0 to 1. Like that. Let's see if he showed it. Yeah. So there I now have a thin line, the thin blue one here. Now, if you want to make an animation, you can change some of the properties for this object. This is now, in MATLAB's eyes, it's a graphical object, this straight line. And when I programmed it, I didn't just write line. Same if you are going to make a curve, you don't just write plot. You give him a name, as I did here. then let's see, where is it? Here. I didn't just write line, I wrote h equals line. Now this big H, that's a handle, sort of a pointer into this graphical object. And this H will now have a whole bunch of properties which you can play around with. So if you now write get H, get this handle, then you get a long list of different things that you can now play around with. So all of these properties for this graphical object you can play around with, you can change during your simulation. So here the line style, that's a straight line, and the line width is 0.5. If you want to change anything, you now write, say I want to have a thicker line here, line style, that was, okay. Then I write not get but set for H, and then use the exact syntax, line, now what was it, line width, width, like that. And instead of 1/2, which is the default, I want to have a line of size of thickness 10. And you execute it, and then you will have now a line which has become much thicker. So during the simulation you can change the color, the thickness, and not to mention the position. And of course that is what I have done here. This is actually just one line from here to here, but it's very thick. And then I just change the Y position during the simulation using this get and set concepts. So you'll see for the here X data and Y data. You just change the values for these matrices, X position and Y position during the simulation. Then you need in the code, that's important, you need a sentence that reads draw now inside the loop. I can show you, where is it? Here we have everything, and here we have the time loop, and here the calculations, solution of these equations. Here I actually used second order, not a first order Euler scheme, never mind that. But here you see I have now set for 5 different lines, and I changed the Y data. And then I need a draw now. MATLAB is lazy. If you don't tell him draw now, he doesn't do it. Then he just waits until the program is finished, and then he draws everything. Lazy bastard. So you have to tell him draw now. This frequency response, this is typically the way you will play around with it here in practice. Start with a step, just give him some noise, and then let him sort of have his own freedom displaying or showing you the natural frequency. Then later you can try with a harmonic input at different frequency to check the frequency response. Now, for those of you who has had regulation already, this actually should be familiar. How to see this input. It will sort of be the question then of, say, the amplitude for your system. And in my in my example here, it will be then the amplitude, the displacement here for the mass, how high will he move, divided by the amplitude of my input signal. So there we are talking about an amplification factor. If he's 1, then you send in a signal here with amplitude 1 meters, and then the system will have an amplitude with roughly the same. And to investigate this, we have to do several simulations. Here, I now do a lot of simulations at different frequencies. And then I just compare the ratios here with the amplitude for the mass versus the amplitude for the input signal. So here I now have gone through a whole bunch of different simulations, different input frequencies, starting with very, very low. Then you see the magnitude here, the amplification factor is 1. I mean, the mass is just moving parallel with the ground. It has the same amplitude, so he'll be 1 until you start hitting the natural frequency to the system. And here I've chosen all numbers to be 1, so the natural frequency will be 1. So here he explodes, actually. I just have organized it so I don't hit 1 directly, or else everything will explode. And then when you continue, the motion for the mass, the amplitude for the mass is getting smaller and smaller. I mean, the input is so high frequent that the mass hardly moves at all. So it's just going down and down and down. I don't get the analytical exactly here due to the numerics, but never mind that. From standard regulation and control theory, you will then use, of course, Laplace transform. This system here is a linear system. Yes, you can create here a double derivative, a second order differential equation, and then you can find the what's called the Bode diagram directly to get this frequency response, the gain, the amplification factor analytically. And you can do that in MATLAB. It's actually just one sentence or a couple of sentences in the code. I think I have it here. Yeah, so you have an option here to give him the input of your equation, how he looks, and then you just write Bode, finished. Then he will provide you with the solution and print it out on the screen. And the solution, then the transfer function, is given here in Laplace 1 over s squared plus 1. So you have a lot of tools with Laplace, yes, and quite fancy as well. I will not pursue this in this course. You should, of course, be aware of it, but we are not going in that direction. And why? It's 2 reasons. One, some of you have taken this course already, so you know this, so it's boring. Second, if you want to do a Laplace transform, your equation system has to be linear. What if you have something like this? Forget it. You can't use Laplace transform. It's not a linear equation anymore. So, and that will happen frequently with our problems. They're not linear. Of course, you have a lot of tricks. You can linearize things and then still use Laplace. Of course they do. But, I mean, that's a different topic. So, no, we will use our our bond graphs, we will not use the Laplace transform. What we are going to do with this cute little example is to continue with control. Now we are just talked about response. You give him a signal and see what happens. Okay, but now I want this mass, he should move in a certain manner. I want him to say he should be constant for a while, and then he should climb slowly up here, and then he should be here, and all of a sudden he should be down here. Okay, if this is sort of the time behavior for the mass, the one that I want, how do I have to move this plate to get this motion correctly? Then we are talking regulation. And that will be the topic for next week, PID regulators. And we are going to use this as an example. So you will see more of this, mass. The final plot, it was so cute that I had to show it to you. Sort of encircled the heart. I just pick, actually I took just one arbitrary frequency here, frequency ratio of 1.5, and did one simulation. And then you make a plot of position versus velocity. So then you have what's called a phase plot. And I mean, it was so nice with the heart there. So I know I really liked it. I think I had another one with, you can just play around with the different frequencies. You can see for yourself. Here omega was 3/2. If we take omega 1/2, we got another one. So the other graphs will be the same. He compares quite nicely here with the analytical solution, but with the high frequency I don't get it correctly. It's very small differences, you don't see them even. But here now you see you have 1/2, so it was 1/2. So see if you can get any cuter than that. Okay, any questions? Then we stop here.